Hello everyone. Today we'll be solving the problem Kyoya and colored balls. Right. So this was asked in the code forces around 309 for the division 1. Right. So let's try to solve Kyoya and colored balls. Right. So here you can just go through the question. Simple question, right? Only 3 lines. You can just go through the question. It's very easier to understand basically. So I'll just summarize the question so that it will be easier for us to solve the problem, right? So what does the question state here? There are k colors. Just keep this in mind. There are k colors, right? So there are k colors and color I has C. One more thing. Color I, what it is having? Color I is having color C, right? That is nothing but this one, CI, right? So indistinguishable balls, that is total less than or equal to 1000. So this is from the constraints basically. So we draw all the balls in some order until the bag is empty. Again, we have to draw all the balls in some order until the bag is empty. Just keep this in mind. That's all we need to do. There are k colors, right? So here there are k colors. I has ci indistinguishable balls, that is total less than or equal to 1000. That is accordingly with the constraints. See here, this one, right? uh, Again, I has ci, nothing but indistinguishable balls, total less than or equal to 1000. We draw all the balls in some order until the bag is empty, right? So constraint here, the last ball of the color 1 appears before the last of color 2, means before and so on, before the last of color k, right? So accordingly with this one, this is fine. You can just go through that one. So we have to count the number of valid draw orders satisfying that last appearance order. What we need to count here, mainly the number of valid full draw orders satisfying that last appearance order. So this is very important, right? So our goal is to count the number of valid full draw orders satisfying that last appearance order. And what we need to output, so we have to output the number of valid full draw orders, right? So just keep this in mind. Also, we need to output the count modulo, nothing but they have given here 10 to the power of, mm, just give me a second here. This is basically 10 to the power of 9 plus 7, I guess, right? So I believe so. This value basically, yep. 8 times 0, it has to be 368. Yeah, same. So this is the question part basically, right? So we have to count the number of valid full draw orders satisfying that last appearance order, right? So all we have is k colors. So k colors, we should be having that k colors in the input as well. And we have color I that has ci, nothing but indistinguishable balls, that is total less than or equal to 1000. So we have to draw all the balls in some order until the bag is empty. Constraint, you can just go through the constraint, and we have to count the number of valid full draw orders satisfying the last appearance order. Also, we have to output the count modulo value, this one they have given here, right? So just keep this in mind. So we can just make use of this one modulo value in the code, right? So this is fine. Yeah, let me copy this one, or let's type it. We have 8 zeros and a 7, right? 10 to the power of 9 plus 7. So this is fine, man. Now let's come to the input output part here. So this is nothing but the k accordingly with the question. So this is nothing but the k. There are k colors, right? So we have 3 colors here, nothing but 2, 2 and 1, right? So this is nothing but the C here, right? So C, this is nothing but the color I has C indistinguishable balls they have mentioned. So this one is nothing but the C here. One second, just give me a second here. One second, man. Yeah, let's continue. So this is nothing but the C. We have 2 to 1, right? So and this is K. This K is nothing but the 3 here. So let me write this down. One second. So why this is not opening? Yeah, this is fine. So this is nothing but K, and this is nothing but C here, 2 to 1. It's fine. The output that we need to get here is 3 1. Simple, this part. So output is nothing but the number of valid full draw orders satisfying the last appearance order, right? So same goes with here as well. See, k is 4, we should be having the 4 this one indistinguishable balls here, 1 2 3 4, and the output that we need to get here is 1680, right? So one thing before discussing the approach, as we are done with the question part and the input output part, so before discussing the approach, I just want to tell you that we'll be going with a DP, right? So DP, along with the, for the optimization purpose, we'll be going with a modular exponentiation as well as modular, this one, what do we call modular inverse, right? So I have the template for this. Still, let's type this one for the from the what do you call scratch. Basically, let's solve this one from the scratch. So we'll be going with the formats theorem basically for the modular inverse, and we'll be going with a modular exponentiation as well, right? So just keep this in mind. So basically we'll be going with a combinatorics as well, NCR. So just keep this in mind. Combination of all this. Basically, main thing is DP here. We'll be going with a DP. Right. So let's discuss the approach followed by the complexities, and then let's write the code, man. Fine. Yep. Let me delete this one. Let's discuss the approach first. So I have considered the same first example that they have given in the question here, right? So this one is nothing but the k. We know this. This one is nothing but c, right? So the value of c here I can just write it in this way in the form of array 2 to 1. So the output that we need to get here is 3, right? So let's see the step-by-step explanation here. So first let's discuss the idea, right? So then we can discuss the calculation, and then in the code we'll be making use of the this one dp as well as the modular exponentiation with the this one modular inverse along with the ncr, right? So we can just go with the combinatorics as well. So this one, first we will build the colors one by one accordingly with the colors. So we have k colors, right? So first what we will do in input, so we have considered k equals 3, and this one c equals 2 to 1. So we will build colors one by one, placing the next colors balls into the growing sequence, right? So just keep this in mind. We'll build colors one by one, placing the next colors balls into the growing sequence so that its last ball is fixed after all the previous colors last balls, right? So this is simple, right? Simple theory. So next, when adding the ith color, so when adding the ith color with c, means in the sense ci, so when adding the ith color with the c balls after having s balls already, the number of ways is this one, c of s plus ci minus 1 ci minus 1. So this is the formula we'll be making use of. Just remember this one, right? So this will be handy. So this will be making use of this one throughout the this one what do we call code, as well as for the calculation part next we'll be making use of this itself, right? So when adding the ith color with c balls, with the c basically balls after having s balls already, the number of ways is c of s plus ci minus 1 ci minus 1 ci minus 1 ci minus 1, same this one here, this one is same, but we'll be adding s, right? So for the first this thing first part, right? So let's move on with the this one calculation part. So we have k equals 3 and this one c equals 2 to 1, right? So 2 to 1. So after color I, nothing but after color 1, here in this case we are considering 2, right? So base equals c of s plus ci minus 1, right? So s plus ci minus 1 here, nothing but 2 minus 1 comma 1, right? 2 minus 1 comma 1. So this one will be 1 comma 1. So sequence length equals 2. Sequence length s equals 2 here in this case, right? So after color 2 of 2, after colors 2, because again we'll be moving on with the next one, right? So we have to multiply by c. So this one will be 2. We have 2 minus 1. This one we have to add s, basically s plus ci minus 1. So this one will be c 2 plus 2 minus 1, and again this remains 2 minus 1. So basically 3 comma 1 will get, right? C of 3 comma 1. So this will be 3, right? So sequence will be 4. Quite obviously, one extra sequence will be quite obviously 4, as we are starting from the 0. Sequence will be 4 here in this case. This one will be sequence will be 2 because we got 1 here. Sequence will be 2. Here sequence will be 4 quite obviously, right? So next we have to go with the color 3. So we are done with 2 comma 2. Now we have to consider 1. So again we'll be multiplying by c and the same formula here. So this one will be 4 minus 1, 4 plus 1, sorry, s, sequence the last previous sequence, right? So see here, this sequence, s plus ci minus 1, whatever this we have done, this one is nothing but 2, previous sequence, right? So 2 plus, 2 minus 1 into 2 minus 1, 2. This 2 is nothing but this came from this one. We are considering this one, right? So 2 to 1. First we considered this 2. See here, 2 minus 1 and 1. So this time 2 minus 1 and 2 minus 1 only will go. So this will be 1, right? Sequence will be 2 as we are starting from 0. So here this 2 came from this sequence. Previous sequence was s, nothing but s. Previous sequence was 2. So we are considering 2 plus 2 minus 1, 2 minus 1. So here we'll get 3 comma 1. So we'll be considering 3. C of this one. 3 comma 1 is nothing but 3, and sequence is nothing but 4, as it starts from the 0. Again we are left with 1. So previous sequence was 4. We will be going with a 4 plus 1, s plus sc this one, ci minus 1, ci minus 1, right? So in this case we have the number 1. So this will be 1 minus 1, 1 minus 1. So here it will be 4 comma 0, right? So 4 comma 0. So this will be basically sequence we have is 1. Sequence we have is 1. So what we got here, output. So this one will be considering, basically output we got here is 1, and c of 3 comma 1, this one 3, and this one is nothing but 1, right? So this one, the product is nothing but 1 into 3 into 1, right? So product, this one is 1 into 3 into 1. So the output will be 3. Output will be 3, right? So the output that we got here is 3, which is equivalent to the output that they have mentioned for the output, sorry, they have mentioned for the example 1 output, right? Which they have mentioned in the output in the example 1, or the input 1 within the question. So our approach works absolutely correct in this case. So as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity here? The time complexity would be big O of t square plus t log mod. So t here in this case, this one ci, right? So t is nothing but the ci, which has to be less than or equal to 1000. So in the question they have mentioned strictly, right? So as we are making use of the dp will scan up to current total each color, nothing but it is almost equivalent to the t square, right? Each multiply step uses NCR with the inverses, as we will be making use of the NCR with the modular inverses. We'll be going with the modular inverses, as I've said. So each multiply step uses one NCR with the inverses, nothing but it is almost equivalent to t into log mod, right? So overall time complexity would be big O of t square plus t into log mod. So this is fine. So what will be the space complexity here? The space complexity would be big O of t for the DPRS, nothing but size 1001 plus big O of k for the input counts, right? So overall time complexity and the space complexity for the code that we'll be writing in the future would be big O of t square plus t into log mod, and big O of t for the DPRS, and big O of k for the input counts, nothing but the space complexity. So as we are completely familiar with the approach and the complexities part, we are good to write the code. Let's start writing the code. So let's start writing the code, right? So I'll just come to the compiler here. First, what we'll do, we'll be making use of the different this one, fast input and output. So I'll just import here input output package. So I'll just go with java.input output.star. So this is fine. So now let me consider class here, public class. So I'll just go with main. This is fine. So I can just give any class name that's relevant to the problem. You can just give the question name or something, right? So basically that's relevant to the question. So I'll just go with main here. First step is they've strictly mentioned in the question we have to go with the modulo. They have mentioned the modulo value, right? So let's go with the modulo as required by the problem. And so I'll just go with static here. This one final, and so I'll just go with a mod. So 1, this one 7. This is fine. Now, the next step would be, as I have said, we'll be going with the fast modular exponentiation. Nothing but we will be computing a to the power of e mod, the main value mod, right? So I'll just go with the static here. So this one will be long. I'll just write this one is modular exponentiation, right? Mod power. So I'll just give mod power here, right? So let me go with the uh, two this thing. What do we call? Parameters. One is a and another one is e. So within this method, mod power. So first let's go with the result variable that will accumulate the answer, right? So I'll just go with the long result. Let me initialize this one to 1 and let me go with the simple while loop here. So while e greater than 0, so this one I'm speaking of, while e greater than 0, meaning we are just looping over bits of the exponent e, right? So I'm making use of the simple while loop here. So here let's make use of the if condition, means if current bit is 1, then let's multiply by a. So I can just write it in this way. If current bit is 1, in the sense I'll just go with e, uh, current bit is 1, right? So I'll just make use of a percent here, and 1, this is equivalent to 1, means if the current bit is 1, then we have to multiply by a. So I'll just go with here, mm, result equals result into a, uh, modulo. So we have to consider mod value, right? So I'll just go with the mod. We have assigned this one to the embody. So this is fine. Next part here would be we have to square the base each step, meaning here I'll just go with a equals a into this one, a modulo mod. So this is fine. After squaring the base each step, let's shift the exponent right by 1 bit. So e I have considered, I'll just go with right shift 1 here, right? So finally let's return the result. Nothing but we have to return a to the power of e, a small mod and the mod, right? So I'll just return result here in this case. So let me go with return result. So let me come out of this one entirely. Now let's go with a modular inverse, right? So we will be going with a this one. We'll be making use of the Fermat's little theorem. So you can just go through the theorem. So this is very simple. As I've said, during the approach itself, we'll be going with the Fermat's little theorem, or Fermat's theorem, I said, I believe. Right. So now let's go with the modular inverse using Fermat's little theorem. So whenever for the number theory, or whenever you want to solve this one using the modular inverse or the modular exponentiation, it's better to go with a different template basically, right? So it will help you a lot when it comes to the optimization part, right? So that's one of my opinion. So now let's go with the modular inverse using Fermat's little theorem. Nothing but x to the power of mod minus 2, mod value, right? So I'll just go with static here, long. So this one will be mod uh, inverse. Let me go with the long x. I need the parameter x here. This is fine. So we have to make sure that it is valid since mod is prime, right? So I can just return in this way. Return. We have written mod power already. So we'll be making use of the mod power method within mod inverse or the modular inverse method, right? So I'll just go with x comma, so we have to give mod value. This one is mod minus 2. Simple. So we have to make sure that it is valid since mod is prime, right? So this is fine, man. We are done with the modular inverse basically. To make use of the modular power, so this one modular exponentiation, we have written the extra helper method called modular power. This is nothing but the modular exponentiation. This we are making use of it within the modular inverse basically. So we are this is nothing but we are making use of the Fermat's little theorem. Again, x to the power of mod minus 2 mod and mod value, right? So this is fine. Now as we are done with this part, so let's do one thing. Let me go with the ncr modulo mod, right? So that will be computing on the fly. And again, I just want to tell you one thing. So here r will be chosen to be small side, right? So let me write it in this way. Static, so this one will be long. So let me give ncr. So as we are making use of ncr, so I need the parameters n and r basically, right? So within this method, so first let's go with the invalid choose, right? So suppose if r is less than 0, or this one r is greater than n, then let's return 0. Then let's return 0, right? So now let's go with the accumulator. Nothing but let me assign the result to 1. This is fine. Let's go with a simple for loop here, meaning let's multiply the numerator and divide the denominator, man. Right? So let's simple. This is very simple. So I'll just go with the for int I equals 1. So I less than or equal to r, so this one will be I plus plus. So this is fine. So within the for loop, we have went with a multiplying numerator and the dividing denominator, right? So in simple terms, we are going with the iteration pattern. So let's move on with the further steps. So within the for loop, we have to multiply by next numerator term. So I can just write it in this way: result equals result into, so this one will be n minus r plus this one I. So again, let me go with the modulo mode. So this is fine. Next step, finally we have to multiply by inverse of I, nothing but the denominator, right? So as we had discussed earlier, so this one will be again result into mod inverse. This is fine. So this one I modulo, so this one will be mod. Fine. So we're just multiplying by inverse of I, nothing but the denominator. So now let's do one thing. Let's return the result, meaning we have to return C of n comma r mod value, right? So I'll just go with return, let me return the result. Fine. So now we are done with the helper methods. Let's come to the main method, and also we have to implement this one input output as well, right? So I'll just go with main here. So this one, let me delete this one. So let me make use of throws exception, this one exception as well, or else we'll get the error. So let me go with exception. This is fine. Now let's do one thing. Let's go with the fast input reader, nothing but buffered reader here in this case. Buffered reader pr equals new buffered reader. So this one will be new input stream reader. So this one is coming from system dot n. So this is fine. Now let me we have to read the number of colors, right? First in the input we have been given k. So I'll just go with k equals, so integer dot parsen. So this will be buffered reader dot read line. So this is fine. Next step would be, let me go with balls. So I'll just go with balls here. So this one, let me assign this one to new into. Okay, we're just going with the initialization part. So this is fine. Finally, let's go with the iteration, right? So we have to read each C of I, or Ci basically, not C of I, C basically in simple terms. So I'll just go with for I equals 0. So let me write this one quickly. I less than k, I plus plus. So this will be iterated value of the balls, that is equal to integer dot, this one will be percent, and this one will be buffered reader dot read line. So this is also fine, man. Yep. So the next step would be we'll be initializing the DP array, right? So we have discussed this one during the approach itself. We'll be going with the DP of S. Basically, it's nothing but ways of the processing some colors having total S, right? So I'll just take the size DP array of size 1001 accordingly with the constraint, right? So let me go with long here, DP equals new long of, so I'll just consider 1001. So this is fine. Now let's go with the base case, nothing but we are going with the zero colors, nothing but one empty arrangement. So I'll just go with DP of 0 equals 1, and also let me initialize total to this one 0. This is fine. Nothing but we are considering total balls that is processed so far, nothing but prefix some s here in this case, right? So next let's move on with the for loop. So I'll just go with for here. So let's process each colors count, nothing but see here. I'll just go with int count. So this one will be balls, right? So this is fine. So within the for loop, so we will be going with the next DP layer for updated total. So I'll just go with long. So this one will be next new. This one will be long. Size we have considered 1001. This is fine. Now, as per the approach, we have to iterate over the all the possible previous totals that has been used from 0 to s, right? So how can we do that? Let's go, or let's move on with the iteration part here. So this one I can just write it on this way. I'll just go with the used keyword here. 0 used, it has to be less than or equal to total that we have already considered, and let me increment used here. This is fine. So within the for loop, so only transition that exists from the states, right? So only transition from states that exist that we need to consider, right? So here in this case, so this is fine, man. So within the for loop, what we need to do, we need to go with the new total, right? So if you remember the formula, in every step in the approach, we went with s plus ci minus I, right? Ci minus 1 basically. So this one, how can I write it in the form of code? So I can just go with new used. So this one I can just give here used plus count, right? So this is fine. Now ways we have to consider all the ways to insert this color with the last ball that is fixed after the previous colors, right? So I'll just go with long ways, right? So this one will be ncr of new used. So this one will be -1. So this one will be count -1. This is fine. Yeah, finally, let's accumulate the modular value. So I'll just go with next here. So let me make use of new used here. Let me assign this one to next. This one new used plus dp of, let me go with used uh, into ways, right? So this is fine, man. Modulo, this is fine. Next, let's do one thing. Let me assign dp to next. So this is fine. And also let's update the total balls that is processed. So I'll just go with total equals total plus count. So this is fine. We are left with only one part, nothing but finally we have to output the answer. That is nothing but that is the ways when all the balls are basically used. That's what they have asked in the question as well. So I'll just go with the system out println here. Let me give dp of, we have already total, dp of total, right? So this is it for the coding part. So before checking the code with different this one inputs, I just want to copy paste the signature starter template. Just give me a second here. So I'll just come here, let me paste this one. Let's concentrate on the logical part, right? So I hope this works, man. Let me come here, let me copy this one. The output that I need to get here is 3. Let's check. So we have some error here, the line number 30. So what is the error? Error, not a statement. What happened to this one? Just give me a second here. Uh, in A and E we have considered here. There is a yeah, E greater than 0. So we are going with, if current bit is 1, we are multiplying this one by A. This is fine. Modulo mod A equals. Oh yeah, I have forgot to give equals here. This one we are just making use of the shift component, right, by 1 bit, right? So I have to give equals here. So this error has to be gone now. Yeah, now we have error in the line number 73. Identifier expected. I'm just going with a mm, this one. I'm just going with a DP. This one, right? Total. What's wrong here? Huh, comma. Why system out println I have given. This is fine. Uh, DP of total I'm considering. So this is fine. Total equals total plus count. This is also fine, man. I still don't understand what is wrong here. Mm, so let me delete this one. Also, let me give this again. I don't understand what's wrong. Just give me a second here. So what mistake I have done here is, so this one, let me come here, for loop. So I have forgotten to mention the if condition here. So I have directly written the new total. That is nothing but, so in the approach that we had discussed this one, right? S plus C minus I, Ci minus this one basically. That I have went with this one directly. So we have to write the if condition, right? So we have to consider only transition from the states that exist basically. So I said that one, but I didn't write the if condition at all. So this one has to be dp of used here. I have to consider if not equal to 0, right? So this is fine. Now we have one more, this one flower bracket here I need to consider, right? So this is fine. Now one more thing is here, next of new use, this has to be within the array, not within the parenthesis. So this is fine. Now let me run this one. Yeah, we are getting the correct output, right? See, 3, right? So we are getting the perfect output. So now let me go with the second input. We have to get the output 1680. Let's check. So we are getting the correct output 1680, right? So this is fine. Now let me copy this one. This is fine. Let me come here. Let me submit the code. Mm, let me choose the problem A here. Let me paste the code and let me hit the submit button. So I hope this works for all the test cases, man. Let's see. Let's wait for some time. Let's wait for some time. Yeah, you can clearly see here, right? So the verdict that we got here is accepted, right? So again, we have went with a DP, simple DP, right? So DP array of size 1001 along with the mod value, right? So basically we have made use of the formats theorem, nothing but here we have went with a modular exponentiation along with the modular inverse and NCR, right? So we have made use of the simple DP within the main logic as well, right? So this is fine. I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.